Okay, does everyone know about prime numbers? And if you know, can you give a one-liner definition of prime number? What is a prime number? Yeah, so prime number is that kind of number which just has two factors, and those two factors are 1 and the number itself. Okay, so if you have a number like 7, the only two factors of 7 are 1 and 7. Okay, so 7 is a prime number. Okay, is 1 considered as a prime number? 1 is not considered as a prime number. Reason is that because 1 just has one factor, which is 1 itself. So there is no second factor. And the criteria for prime number is exactly two factors. Exactly. Okay. Which is 1 and the number itself. Okay. Now the question is simple, that you have to basically check if n is prime. You have been given n and you simply have to check if n is prime or not. So how can I do that? You can simply, yeah, as easy as that. You can simply iterate from the smallest prime number, which is 2, and go on till the square root of n. Okay, and just try to check whether you are getting a factor of it or not. So if you simply write a for loop where you iterate from 2 to square root of n. Okay. Now if you found out that none of the values of I in between 2 to square root of n perfectly divides this n, then you can easily say that this n would be a prime number for sure. Is this clear to everyone? Did everyone follow this? So simply iterate from 2 to square root of n, and if you could not encounter any value of I which perfectly divides, then you can answer. So what will be the time complexity of this approach? How much time is taken over here? It would be order of square root of n. So given a number n, and to check whether it is a prime or not, the time which I am taking is order of square root of n. Now if let's say you have to print me all the primes that are smaller than equals to n. So now a number n is given, and now my aim is to print all the primes that are smaller than equals to n. So if you try to solve this problem, by this I mean, let's say the value of n given to you is 10. So the values that you need to print should be 2, 3, 5, 7, that's it. These are the prime numbers, okay, which are smaller than equals to 10. So how much time will be taken over here to solve this problem? So think of it in this way. Think of it in this way. How many numbers are there for which you have to do primality testing? I call it primality testing. This thing. You have to perform primality testing for all the numbers from 1 till n. Can I say that? You will perform for all the numbers, and right now we saw that what is the maximum time that can be taken for any number to check whether it is prime or not. You iterate till square root of that number, right? So the maximum time taken for any number in between this 1 to n would have been something like square root of n. So we can say that an upper bound on the time limit would be total number of elements for which primality testing is being made, which is n, multiplied by maximum time spent on any number, which is square root of n. So the time complexity of this will be n into root of n, which is order of n raised to power 3 by 2. So if you have to perform prime testing of numbers from 1 to n, then going by this approach you will take this much of time, which is n raised to power 3 by 2. Okay, now under certain cases this is a lot of time, okay, because if the value of n is, let's say, something like 10 raised to power 6, okay, then for 10 raised to power 6, if you use this formula, you will end up seeing that there are about 10 raised to power 9 operations, and if there are 10 raised to power 9 operations, your code will time out, okay. So there has to be a better way of doing this, yes, and that way, some of you might have heard it, this is called as Sieve of Eratosthenes. So I'll start it from scratch. This is a very interesting algorithm, okay, so focus your attention on the board completely. So it is said as something like Sieve of Eratosthenes. Okay, what is the meaning of this word sieve? Can somebody tell me what does it mean? You can quickly Google it if you want. What does a sieve mean? I mean, literally. So yeah, sieve is like a filter. Okay, so sieve means a filter. So there is a filter, okay, where numbers are poured, okay, and those numbers are from 1 to n, and only those numbers which are prime, they pass through this filter. So this algorithm is exactly like this filter, that it will take in all those numbers from 1 to n and it will allow only the prime numbers to pass through. So whatever residue you get, I mean after filtration, then whatever is not filtered, those are composite numbers, and whatever got filtered, those are prime numbers. Okay. So how does it work? I'll try to tell you that. Its working is very simple. Let's say I have to find prime numbers from 1 to n and the value of n is 20. Okay. So I want to find that how many numbers are prime in between 1 to 20. So how's that done? Yeah, so that is the concept. So how's that done? Let us take a look. I'll first write all the numbers from 1 to 20, which are 1, 2, 3. Now, the way this algorithm runs is that it maintains two classes of numbers. So the two classes are, first class is the numbers that are crossed and second class is the numbers that are not crossed. Okay, numbers that are crossed and numbers that are not crossed. Now the way it runs is that the first non-crossed number is always prime. First non-crossed number is always prime. This is how it works. So can you tell me, can I say for guarantee that the first number, which is 1, will definitely not be prime? Can I say that? I can always say that. First number 1 is definitely not prime. So can I put a cut mark at 1? I can do that, right? So I can put a cut mark at 1. Now out of all the numbers that remain, can you tell me which is the first non-crossed number? Which is the first non-crossed number? That is 2. And is 2 a prime? Is 2 a prime? Yes, 2 is a prime. Now what happens when you encountered a number which is non-crossed number, that is a prime? Now can I say that all the multiples of a prime will definitely be non-prime? Can I make this statement? All the multiples of a prime will definitely be non-prime, and by multiples I exclude one multiple, okay, because multiple of 2 is 2 also, but I don't want to consider one multiple. I want to start considering from 2 multiple, which is 2 into 2, 2 into 3, 2 into 4 and so on. Are you getting the point what I'm trying to say? So all the multiples of 2 which are not 2 itself will all be non-prime. So what will I do? All those numbers which are multiples of 2, I will cross them. So I will cross this 4, I will cross this 6, 8, 10, 12, 14, 16, 18, 20. Okay, done. Okay, so I am done with this much of part. Now the part that remains, which is from 3 to 20, which is the first non-cross number in this part from 3 to 20? 3 is the first non-cross number. Who said 9? It's 3. 3 is the first non-cross number from 3 to 20. And can I again say that 3 is a prime? Yes, 3 is also a prime. So now what I can do? That for this 3, whatever multiples of 3 are there, I'll cut them. So the multiples of 3 are 6, which is already cut, so no need of cutting again. 9, it is not cut, so I'll cut it. 12, already cut, so no need to cut. 15, I'll cut it. 18 was already cut. Okay, 21 does not exist. Okay, so now I am done with this much of portion. Okay, now which is the first non-cut number? 5, and 5 is a prime. Okay, so how many of you can realize this thing, that the first non-cut number that I happen to see, that number is a prime number? Can you realize this thing in this algorithm? What will happen when you reach 5? When you reach 5, what will you do? you will say that I will want to cut all the multiples of 5, which are 10, 15 and 20. They are already cut, so no need to cut again. Okay, so now you will move on. So the basic point over here is, guys, that whenever you are at a number such that that number has been cut, then no need of doing anything. Are you getting this point? No need of doing anything if that number has been cut. Only if that number has not been cut, it implies that that is a prime number. So what would you want to do? You would want to cut off all the multiples of it which start from 2. I mean all the 2 multiples, 3 multiples, 4 multiples, 5 multiples of that number. So this is the way in which Sieve of Eratosthenes run. So you see it very clearly. For 5, 10, 15 and 20 were there to be cut, which are already cut. 6, you will ignore 6 because 6 is cut. 7, so for 7 you will see that the multiples are 14, 21 doesn't exist. Then for 11, multiple doesn't exist. 13, multiple doesn't exist. 17, 19. So whatever numbers you are left with, okay, those numbers are the prime numbers. So how many of you understood this thing? Just say yes, those of you got it. Okay, and now let me tell you why does it make sense, why does it work. The reason it works is because if you have, let's say, processed these many numbers, and let's say you arrive here, which is a number 5. Now, I told you that if there is any number n, there must be at least one factor of it which comes before square root of n. Okay, and currently you are at n minus 1. So n minus 1 is definitely greater than square root of n minus 1. Sorry, is n minus 1 is definitely greater than the square root of n. So if you could not happen to see a factor of this till this point, that is the reason it has stayed alive, that is the reason it has not been cut. That definitely means it is prime, and using it I can cut all its multiples. See, maybe I'll clear one more thing up over here. Let me tell you one thing. Whenever you arrive at a number that was cut by something, then you simply ignore it and jump on to the next number, isn't it? Yes, no, isn't it? Whenever you cut a number, whenever you arrive at a number which is already cut, you ignore it and move ahead, right? Why do you do that? Why don't you cut the multiples of this 4 also, which were 8, 12 and 16? Why don't you do that? You don't do that because those would already have been cut by that number which was responsible for cutting 4. Because if there is a number 16 which is a multiple of 4, okay, and if 4 has been cut because of some number like 2, then this 2 would have cut this 16 also. Because if 16 is a factor of 4 and 4 is a factor of 2, then 16 would be a factor of 2 also. That is the reason whenever you arrive at a composite number, you can simply ignore. Is that clear to everyone? The reason of ignoring the composite numbers? Because their multiples would already have been cut by the factors of 4 itself. Okay? Okay, cool. So tell me one thing. Now let us try to simply comment on the time complexity of this algorithm. So let us do that one by one. So this 1 is trivial because 1 was cut initially and then I started my journey from 2. Okay. So when you were at 2, you basically ended up cutting all the multiples of 2 from 1 to n. Can you tell me how many multiples of 2 will be there from 1 to n? It should be n by 2. So the count of multiples of 2 in between 1 to n should be n by 2. Okay. Now when you come to 3, so the number of operations for this 2 would have been n by 2. Now when you are at 3, how many operations would happen? When you are at 3, number of operations would be n by 3. When you are at 4, how many operations will happen? Okay, somebody fall in a trap. 0 operations, or basically, why 0 operation? Because you will ignore it because this number was already cut. Okay. At 5, how many operations? N by 5. At 6, 0 operation because this was cut. At 7, n by 7. So the series of quantity of operations that you are getting at each step, that is following this kind of pattern. So is everyone clear with this pattern, which is basically denoting the quantity of operations being done at each series? Now if you take n common over here, then what you will get inside is the sum of reciprocal of prime numbers. Can I say that? What you get inside is the sum of reciprocal of prime numbers. Now this is a very interesting series, and the solution of this series is there is a mathematical proof to it. I will not go into details of it because that is not that necessary. You can simply remember what is the value to which this series converges, and if you are interested in mathematical proof, you can take a look, and if you want to discuss it with me offline, I can discuss that. Okay, so the value of this series, which is sum of, I repeat, sum of reciprocal of prime numbers till n, this is equal to log of n, log of n. Okay, so the overall time complexity of this Sieve algorithm is n multiplied by log n, where n is the number up till which we need to find the primes. Okay, can I say that this is way better than the previous approach where the complexity was turning out to be n raised to power 3 by 2? Can I say this is way better than that? This indeed is, right? Because n into square root of n, which you had over there, the previous one was n into square root of n. And we know that log of log n will be even smaller than just log n. So this is a much better approach to find out the prime numbers. Okay, yeah, now let's just go ahead. Please remember about this thing. Now if I have told you about this series, I would also want to tell about one more series. If let's say you get a series like 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7. How is this series different from this series? The other series that you see, that series is the sum of reciprocal of all natural numbers. Can you see that? That is the sum of reciprocal of all natural numbers. Now that series, if let's say the last term is 1 by n, can somebody tell me what is the approximate value of this? The approximate value of this is log of n. Yeah, and that should be obvious because that contains more number of terms, so its value will be slightly greater than the other one. So that is log n and this is log n. Can all of us remember the summation of these two popular series? So take a note of it and remember that, because you will keep getting many such questions where the series being followed is one of these. Okay, cool. So now, yeah, now let us talk about the implementation part of it. So let me help you out with that. So what I can do is, for all the prime numbers, okay, which are for not just the prime numbers but for all the numbers, all the natural numbers which are in between 1 to n, I'll store their status somewhere. So I can easily store their status in a Boolean array or in even an integer array where the values are either 0 or 1. So what I will do to start with, I'll construct an array of size n plus 1 so that it can contain its indices are from 0 to n. So 1 to n falls well within that. Okay. So to start with, what will I do? That, so basically here, primes of I, this thing, if this thing is 1, it means that I is a prime number. And if this value is 0, it means that I is not a prime number. Okay. So depending on what is the value of primes of I, you can tell whether I is a prime or non-prime. So to start with, I can initialize certain values. I can initialize primes of 0 and I can initialize primes of 1. Can you tell me what should I initialize them to? Should I initialize them to 1 or should I initialize them to 0? I should initialize them to 0. Why? Because 0 and 1 are not prime. 0 and 1 are not prime, and I told you that 0 indicates that I is not a prime number. Okay. Now, as I said, I will start my iteration process from 2. Okay, from the natural number 2. So I will start from 2. Okay, and I can go on till the last number, which is smaller than or equals to n, and I plus plus. Okay. Now, when should I start the cutting of numbers? I should start the cutting of numbers only if the ith number is prime. Okay. If ith number is not prime, then I can simply ignore. So how do I check if ith number is prime or not? By simply checking that what is the value of primes of I. So if primes of I is 1, what does it mean? If primes of I is 1, what does it mean? It means that ith number is a what? Ith number is a prime number. Now if ith number is a prime number, then I need to cut all its multiples. So how do I do that? I will start with its second multiple. So for j equals to 2, this j denotes jth multiple of I. Okay, and I'll go on till my I into j is smaller than equals to n, and I'll keep doing j plus plus. Okay, and what I'll do is primes of I into j equals to 0. So this is the cutting part. So when you were at I equals to 2, you saw that primes of 2 was equal to 1 because initially you had initialized all the values as 1. Okay, that you must do. You must initialize all the values as 1 initially and then mark 0 and 1 as having value 0. So whenever you reach at 2, you will see that primes of 2 is 1, and now this loop will cut 2 into 2, 2 into 3, 2 into 4, 2 into 8, so on till 2 into 10, which is till here. So all of these values, which are 4, 6, 8, so on till 20, primes of those would be equal to 0. Okay, and this is how this algorithm would go on and on and on. Now, is there a scope of some kind of optimization over here? Can I perform some slight optimization? Although the effective complexity will continue to be n log n, but some optimization can be done. Yeah, and what can be that optimization? That can be done what you are saying, but guys, I'll ask you a simple question. That simple question is, let's say you reach to 5. Okay, let's say you reach to 5. When you reach to 5, the first number that you will try to cut will be 5 into 2, which is 10. Can I say that this 10 was already cut by this 2? Can I say that this 10 was already cut by this 2? So guys, just think of it in this way, that whenever you reach at a number I, then if you are trying to cut I into j such that j is smaller than I, then that value would already have been cut. Why? Because let's say you are at 7 and you are trying to cut 7 into 3. No need of doing that. 7 to 3 is not here. Let's say you are trying to cut 7 into 2. No need of doing that because 7 into 2 would have been cut by 2 as 2 into 7. Right? How many of you are getting this point? Just say yes, those of you are getting this. So this is an important thing to understand. So whenever I am considering a number I, then I can start, instead of starting from I into 2, can I start from I into I? Can I start from I into I? I can do that, right? So the value of j, instead of starting the value of j from 2, I can start the value of j from I. Okay? So the value of j starts from I, and this is how it would go on, and this is how the problem will be solved. How many of you understood this thing, that why did I start j from I? Because the previous thing was very, very redundant. Now, if you take a look at this code, there is one more slight opportunity of optimization, and that is that if you have a particular value of I, then your j always starts from I. So instead of putting this condition, can I replace this by this condition, that as long as I into I is smaller than equals to n? Can I replace this by this? I can do that very easily, because think of it in this way. If the value of I is greater than square root of n, if let's say this iteration happens and the value of I becomes root n plus 1, and then you will start with j as root n plus 1. This thing will sure, the product of these two things will for sure be greater than n. Okay, and there is no number which is greater than n in this range. So you can simply bind your range from I equals to 2 to I equals to square root of n. This is also a way of writing. that I lesser than equals to square root of n. And this is how you can go on, and you will be able to compute all the prime numbers. Just think of it in this way. When you were initially going from I equals to 2 to n, okay, then there would have been a value of I which would have been root n plus 1. Yes or no? Yes or no? There would have been a value of I which would have been root n plus 1. For this value of I, what would have been the first value of j? What would have been the first value of j? This number itself, which is root n plus 1, right? Now, root n plus 1 into root n plus 1. Can I say this thing will for sure be greater than n? Will this be greater than n? So is there a need of considering those multiples, because they don't exist only in your range? So the point is that you can just continue your journey from I equals to 2 till I equals to square root of n, which can be written in this way because your j is starting from here. So these are the two optimizations that you can bring in. This j should not be j plus equals to I, because here I am doing I into j. Got it? Simple to understand. Let's say when your I was 5, first you would want to do 5 into 5, then 5 into 6, then 5 into 7, then 5 into 8. These things are j. So j started with I, and every time j is doing plus 1. Cool. So the time complexity of this popular sieve of Eratosthenes is n log n. Yeah, now let us talk about, so the time complexity is okay. What is the space complexity? Is there some extra space that we use over here? Yes, and what is that extra space complexity? That is order of n. Okay, now let us talk about pros and cons. Pros and cons of this algorithm. So answer me one question. If I tell you that, hey, I'll just give you one number, n, and I'll ask you to check if this number num is prime or not, will you use sieve of Eratosthenes for this, or will you use the square root n based approach for this? You will use the square root n based approach for this, because the square root n based approach here will take just this much of time. But the sieve of Eratosthenes based approach will take num log num, this much amount of time. Which time is smaller, first one or second one? First time is smaller. So if you just have a single query to answer, you will not prefer the sieve approach, you will prefer the normal approach. But if you have got multiple queries, for multiple queries I mean that you have got multiple numbers, a range of numbers, and you have to check whether those numbers are prime or not, then what will you use? Will you still use square root n based approach? No, you will use sieve of Eratosthenes. One more problem with sieve of Eratosthenes is that if I tell you that, hey, get me the prime numbers from 1 till 10 raised to power 10, can you get it? You can't, because you cannot create primes array of size 10 raised to power 10. So that extra space which is being consumed is also a big problem. So keep these things in your mind. What are the problems with the sieve of Eratosthenes? Okay, extra space is a big problem, and also if you just have a single query, then this is an overkill kind of thing. You can simply use the square root n based approach.